All right, back from break. So we're looking at Chapter 7, and just a quick review here. We've introduced the idea of energy. We've said that energy corresponds to something in motion. We haven't really looked at that in detail yet. We also said that energy can correspond to energy stored. And we've looked at examples with gravity, where energy is being stored. And we've also now looked at springs, or starting to look at springs, and seeing how much energy is stored in an ideal spring. And we're deriving a few formulas for that. Now, I don't know how you guys feel. I mean, when I remember, taking physics, freshman physics, my first year in college, and I was pretty good with those first, well, what would correspond for the first 6 chapters for us. So the kinematics was kind of fun, and the force, everything felt very intuitive. I could imagine pushing on something and having it accelerate, and then figuring out how fast it's going. And then I ran into these energy chapters, and that was tough. So energy was more abstract, and so I had a harder time. So if you're experiencing the same thing, I'm completely sympathetic. I'm going to try and make this as intuitive as possible, and I'm going to try and be really clear about how and why energy has why the energies work out the way the formulas work out the way they do. In any case, we had looked at these ideal springs, and we started to ask about how much energy is stored there, and we figured out the energy being stored, the potential energy, could be calculated by finding out how much work we did in stretching out the spring. If we figure out how much energy is being stored, that'll tell us what the potential energy is. So we introduced these ideal properties. Now, springs don't have to behave this way. Springs are more complicated than every spring behaving like minus kx squared. But we went through an integration and said that if we're stretching out a spring or compressing it, we are applying a force given by kx. And if we multiply that by x, actually not just multiply, but we take the kx and multiply by dx. So the force is varying. At first it's easy to compress the spring or stretch out. And then it gets progressively harder. As we compress it more and more, the force we need to keep compressing it goes up. And so we said that could be represented by taking the force, integrating it over a distance. That was a formula that we had just developed a few slides before that. And then integrating from 0 out to some final distance. And that value is 1/2 kx squared, evaluated from 0 to x. And the formula we got for the energy transfer, 1/2 kx squared, we said that is both the energy transferred into the spring and what we call the potential energy of the spring. So we transfer the energy in, and now we're going to label that as potential energy. So let's do an example, right? Here is the energy transfer being done by a variable force, and that's going to be a force acting on a spring. So here is the person pulling on the spring, and they stretch it 3 centimeters. Now, they notice that when they stretch it 3 centimeters, that requires 75 newtons of force. So 75, that's like 15 pounds or something. So the person's really pulling on this spring, and they're able to stretch it a distance of 3 centimeters. How much energy was transferred during that stretch? Now, in part B, it says what happens if we compress the spring. We kind of talked about this. So if it's ideal, then pulling it out requires the same amount of force as compressing it, and it'll represent the same energy transfer since each is 3 centimeters. Let's see how this works. So here is the energy transfer due to force F. Now remember, we're pulling on this, And the amount of force we need to pull with is kx. So it's kx integrated over x from 0 to x. And that's the same formula that we just looked at, 1/2 kx squared. Now we want to stretch this or compress it at 3 centimeters. And I'm not sure what that's from, but it's 3 centimeters. The force here is 75 newtons. Now our formula says 1/2 kx squared. I know what x is. What's k? And so we were not told what the force constant was. We have to calculate that on our own. So we're going to take the formula of F equals kx and say to solve for this, we can take k, set that equal to F over x. Now the force required was 75 newtons, and the stretching amount we got here was 3 centimeters. This is working out to be 2,500 newtons per meter. That's a pretty stiff spring. So 2,500 newtons per meter, that's a lot of force that we would need. Now, we're not stretching it a meter. There's another way to look at this. We could write this as 25 newtons per centimeter, but standard units would be in meters, and so that's kind of what I've done here. Now, the work, or the energy stored then, would be given by 1/2 kx squared. Now, it was only 3 centimeters. The force constant is really big, but we only stretched it 3 centimeters. And it's kind of discouraging, but we only transferred 1.1 joule, just a little over 1 joule of energy, which doesn't sound like a lot. Seems like we should have been able to do better than that. But the spring does not have very much energy stored, and a big part of that, it's just not stretched out very much. So anyway, that's what the energy transfer calculations might look like for a spring as we stretch it out. Now, let's go back and ask about, I want to go back and take another look at the spring. We said that springs in general are not going to behave ideally. We've set up a bunch of formulas assuming a particular behavior. So what if the spring, the force from the spring is not directly proportional? What happens in that case? You go, well, we can take any spring into the lab, and what we could do is we could do a graph like this. We could go into the lab, we could take a spring, and then we could stretch it out maybe 1 centimeter at a time, and then take data on how much force is required to stretch that out. So, you know, you could hang 100 grams onto a spring, measure its displacement, hang another 100 grams, measure its displacement, hang another 100 grams. What that would leave you with is a series of data points, right, that may or may not line up. Now, for the ideal spring, all those data points line up. But for a non-ideal spring, for a more realistic spring, they might not. Okay. Now, the ideal spring model works pretty well for a lot of compressible systems. But if we wanted something to determine more detail, we could collect our own set of data and then generate a curve or draw a curve that goes through the data points. Now, if we do that, how are we going to figure out how much energy we've transferred? And remember that if we plot f versus x data and then draw the function in, the area under the curve will be the energy transfer. That's going to work in any case. So we could draw this on a piece of paper. We could get some scissors. We could cut this out. We could go weigh it on a scale and find out how much area that represents. And that's exactly what, when I was in college, I had a roommate that was a chemical engineering major. He was taking all these engineering classes. And that's what they did in one of their labs. is they took a spring, collected a bunch of data on the spring, and then they took scissors and cut it out and got the mass of that piece of paper. Now the paper was known to have a certain density to it, and so by knowing the mass, they could figure out the area, and then the area was equal to the energy transfer. So, you know, a nice graphical technique where you could go in and map that out. Now today you would probably go into some kind of a software package, plot your data, have the software draw a curve that best represents your data points, and then have the software calculate the area within that curve. So that's certainly doable too. Let's see, this is, okay, this is the example we looked at. Did I go back too far? Oh, I didn't come forward far enough. Okay, here we go. If we write the acceleration in terms of velocity and distance, here's what we find. So we can take the energy that's been transferred, and we can write that in terms of force and distance, and then change that into acceleration and velocity. What we can show is for a constant force that the energy that's transferred is equal to 1/2 mv2 squared minus 1/2 mv1 squared. And we define the kinetic energy for an object as 1/2 mv squared. So we kept saying at some point we were going to develop a formula that would tell us how much energy of motion an object has. And we were going to call that kinetic energy. So here we are. That is our formula for kinetic energy, and I've highlighted that, and that's going to be very, very important for us. Now here their derivation was a little thin. They really just kind of wrote down a formula. So they have a nice picture. So let's talk about the picture first, and then let's look at some of the details of what's going on. So here's a car. It's traveling at a certain speed. It has a certain mass. That means that it has a certain amount of kinetic energy already. It's already moving, unless it happens to be at rest. Now what we're going to do is we're going to have that car speed up. How do you get something to accelerate? Well, you exert a force on it. So what's going to be required is some kind of a net force in the forward direction, and that's going to take it from some velocity here up to some higher velocity over there. So over a displacement, there is a force that acted on the car. It's the frictional forces from the tires and the pavement propelling the car forward, and that is energy transfer. That's work being done. So the pavement is transferring energy into the car by consistently generating a force on the car, pushing it forward. What that's going to lead to is an increase in kinetic energy. So let's take a look and see where this derivation comes from. The derivation it's not so crucial. It's important for you at this point to be able to do, well, the homework problems and apply the formulas. But let's take a look. Let's say that we have an object, maybe this is the car. There's a gravitational force, there's a normal force. Here is the force that's going to create an acceleration. Now, an acceleration could be written as dv dt. We saw that in those early chapters. We can use a trick here, and the trick is to add a factor of dx on the bottom and the top. So, you know, in calculus, a lot of times, you know, students learn that this is taking, dv dt represents taking a time derivative of the velocity, but often students don't realize that the dv's and dt's can just be treated like variables themselves. So dv dt also can be thought of as just a ratio of how much did the velocity increase during a time interval. Increase in velocity, time interval. that ratio tells us what the acceleration is. Now, since they're just like variables, I can add a factor of dx to the denominator, I can add a factor of dx to the numerator, and I can add them in a way and separate them out. I'm going to write this expression now as dv over dx, dx over dt. The dx over dx, that's like a factor of 1. That doesn't change my formula. But now what I can do is I can take the dx over dt and say that's velocity. So I take the dx over dt and I replace that with velocity. Here is the new expression for acceleration. And notice the time is missing. The time's not there anymore. We intend for the time not to be there. The acceleration now is not being written in terms of time. It's being written in terms of displacement. So acceleration, it's dv dt. That certainly works. But in the case of energy derivations, we actually want to use this approach. We want to use v dv dx. And that gives us the acceleration. Okay, so remember this right here. Well, let's follow up on this right now, actually. So let's take the dx, move it to this side, and then let's integrate. What that leaves us with is a dx integrated from x naught to x, and v dv integrated from v naught to v. Now, if, and only if, I guess, the acceleration is constant, then I can take the a outside the integration. But remember, now we're assuming the acceleration is a constant. If I do that, this side integrates out to be constant a times x, evaluated from x naught to x. The right side becomes 1/2 mv squared, v naught to v. This becomes a times x minus x naught is 1/2 v squared minus v naught squared. Finally, we get back to v squared is equal to v naught squared plus 2a x minus x naught, that last formula over there in the right column. That was one of our constant acceleration formulas. So we've derived one of the formulas that we used back in chapter 2, I think it was. All right, now how does that relate to energy? Well, let's also bring in some stuff from chapter 4. There's an acceleration taking place, and we've got that listed over in that far formula. The acceleration is given by force divided by m. And the force then can be written as m times a. That means that the force could be written as m times v dv dx. So this time, I'm going to make use of this expression that I'm not standing in front of. If I bring the dx to this side becomes f dx, and the other side becomes mv dv. Now I can integrate those. I can integrate all of the f dx's together on the left side, and I'm realizing now, oh, the left side of that equation, that is energy transfer. So what we have over here on the left side represents little bits of energy transfer all integrated together. So little energy transfer, little energy transfer, little energy transfer. We add it all together by taking an integral. What's that equal to on the right side? So, the total energy transfer becomes 1/2 mv squared, evaluated from v1 to v2. And what that's going to become is the net energy transfer is equal to 1/2 mv2 squared minus 1/2 mv1 squared. That's kinetic energy 2 minus kinetic energy 1. That is W net is equal to delta K. Okay, and that's what we had up here, right? So we said that anytime we transfer energy, that results in a changing of kinetic energy. If we start out with no kinetic energy at all, then the energy we transfer in shows up as 1/2 mv squared, and that's what we're going to call kinetic energy. What we went through here were all the gory details behind that. If you can follow all this, then great. I hope that makes a lot of sense. If not, let's say don't worry about the details here, but take a shot at it. Take a shot at it and see if all the derivations work. Again, the key thing here is when you get the homework problems and we look at examples in lecture, make sure that you've got those clearly understood. So what we get to is what's called the kinetic energy the work energy principle. The idea is that energy is conserved. If we transfer energy into an object, it's got to show up either as kinetic energy or as potential. Now, if it's the force is being applied, and the force is being applied and the object is accelerating as a result of that force, that's going to show up as additional kinetic energy. And so that's it. It's highlighted. Energy transfer then into that object will show up as an increase in kinetic energy. Or negative, we could have a force working against the motion, like putting the brakes on in a car, and then the net work, if it's negative, the kinetic energy decreases. Those are going to be the possibilities here. All right, here we go. Here is a hammer. Here is a nail. Here's a piece of wood. And so we're hammering on this nail. And what happens every time we strike this is that there's a force acting over a certain distance. They're just saying this is a transfer of energy. I'm not sure if there's a lot that we want to take away from this. I guess what's happening is energy is being taken away from every time the hammer strikes, energy is being taken away. That energy is transferring into the nail. What's going to happen as a result? And they're saying something like kinetic energy, but I think it's a better example for generating thermal energy, right? There's going to be an opposing force. The nail is not just going to take off. The nail is going to be driven into the wood, and as a result, there's opposing forces, and I think the nail heats up, and maybe the wood heats up, the hammerhead heats up. So at all the places where the energy is being transferred in this one, at the end of the day, everything is still at rest, and so I'm going to say everything's going to end up as thermal energy in this case. Okay, here's that baseball example. So this was the very first slide, right, that we started out with the athletics picture. Kinetic energy and energy transfer on a baseball. So here we go. The baseball is 145 grams. It goes from rest to 25 meters per second. Now, 25 meters per second, that doesn't sound very major league. 25 meters per second, that's, that's like, what, 55 miles an hour? Aren't we supposed to have those 90 mile an hour fastballs? Anyway, the baseball acquires a speed of 25 meters per second. What is its kinetic energy? What was the net energy transfer on the baseball that enabled it to reach that speed? So we're just kind of building up a vocabulary here to talk about this stuff. So here we go. Here's the baseball. Remember that pitcher wound up and started from rest and then exerted a force over a distance. And that force acted over some distance. The mass of the baseball, 140 grams. I converted that to kilograms. The final velocity is 25 meters per second. Let's plug that in to our kinetic energy formula. So we're going to use that a lot. The K equals 1/2 mv squared. That's not going away. That's going to get used a lot over the next several chapters. So this is kinetic energy for us right now. Now, I guess it's worth mentioning right now. This is a classical formula for kinetic energy based on Newton's formulas for motion. It turns out that in physics 3b, when we get to special relativity, we're going to find out that there are formulas that are more general that we can use. So this kinetic energy formula works really well as long as objects have mass and as long as they're not going too fast. But in physics 3b, with special relativity, we're going to find out that light has kinetic energy, but it has no mass. So this formula is not how we determine the kinetic energy of light. For photons, particles that make up light, we're going to need to think more broadly about kinetic energy. Now, also, if this baseball starts traveling near the speed of light, then if it's going really fast, we're going to find out the formula here doesn't work especially well. Now, at lower speeds, special relativity still says there's a correction, but it's tiny. But so at the speeds we're working at here, 25 meters per second, 1/2 mv squared works absolutely great. All right. So this baseball is going to acquire 45.3 joules, that's a J, of kinetic energy, and that means that when that pitcher exerted a force, that must have added up to be 45.3 joules. The way that that's being calculated, see if we got the formula here, maybe not. I guess it's here. So well, let me go back and see. Boy, it is way back. This. So if I go all the way back to here, that could be applied to the baseball pitcher pitching that baseball, and because the force, maybe it wasn't constant. Okay. But in any case, that's how we could set up that calculation. Now for us, pretty much all the examples, again, take a look at the homework to get an idea here, but I think all the examples we look at, the energies are going to, the forces are either going to be constant or they're going to be some simple formula like the ideal spring. So that's about the level of complexity we're going to be looking at. All right, let's look at another example. Let's say that we have an automobile. It says that it is 1,000 kilograms. It's a fairly low mass. And it's going to accelerate from 20 meters per second to 30 meters per second. Okay, and this is a trick question. How much work is required to take the car from 20 meters per second to 30 meters per second? And you go, I get this. So work is energy transfer. And that says that we can look at the car before and then look at the car after. And the car has a mass of 1,000 kilograms. It starts out at 20 meters per second and ends up at 30. The kinetic energy that it starts with, I can calculate as 1/2 mv squared. And putting in the 20 meters per second gives me 200,000 joules. So that's 200,000 joules of kinetic energy that we start with. And then here, it's moving at 30 meters per second, and that represents 450,000 joules. So what happened was, I went from 200,000 joules to 450,000 joules. The textbook never actually talks, I don't think, about energy conservation in this chapter, but basically that's what we're coming up to, is that energy is conserved. If I had this much energy to start with, and now I have this much energy, that 250,000 joules must have come from somewhere. And it came from the energy transfer. So the energy transfer here is the difference between these, and it says that the force applied provided 250,000 joules. Now, which force was it? So here's my force diagram. This force F, that's looking pretty promising as far as providing additional energy. Normal force, not so much. Normal force is in the wrong direction. So Wn, so I've got this listed. The W net would come from adding the energy contributions or transfers from each of these. What I could have done here and didn't, maybe I should go back and do that, is this one's going to be 0 because it's in the wrong direction. And this one's going to be 0. That's gone. That's gone. This 250,000 joules could only have come from this, because this force that transfers energy in needs to be in the direction of the displacement. So the only one of those forces acting in the direction of displacement is big F, and so that's where the energy is coming from. Now, that said, this one's 0, this one's 0. What about friction? Well, I'm using friction to make the car go faster, friction with the pavement, but there could also be other frictional effects within the car. There could be resistive effects, air resistance and such, that are tending to slow the car down. Those would subtract, and so this force is going to have to provide at least 250,000 joules, and probably more, because that force forward has to compensate for any of the energy transfers out due to the resistive forces. Okay, so that's the way to think about this. All right, here's another example: kinetic energy and the work energy principle. What about stopping a car rather than making a car go faster? What if we want to slow it down? Well, in this case, what we're saying is we have a car traveling at 60 kilometers per hour, and it puts on the brakes and stops in a distance of 20 meters. If the car now is going twice as fast, what will the new stopping distance be? And assume that the maximum braking force is a fixed value. All right, so here's the idea. I got a car at 60 kilometers per hour, and it stops in a distance of 20 meters, and its velocity finally is 0. That is kinetic energy that we start with, and then the energy has to be taken away. Who's going to take the energy away? Friction's going to take the energy away. Now, when we have the car go twice as fast, what's going to happen to the stopping distance? Now, they've drawn this as if it doubles the distance, but it turns out that's not right. So don't trust the diagram this time around. We better go in and look at the math. So here is the diagram. Now the car is traveling to the right. If you look at that previous picture, I should have put a velocity here. That car is going to the right. Here is a frictional force slowing it down. Here is gravity. Here is the normal force. Gravity and normal force, they're not transferring any energy in this example. They're in the wrong direction. The displacement is going to be to the right. And so it's only the frictional force that's transferring energy, and the frictional force is exactly opposite the displacement, and that's going to give us minus Fd. Now, sometimes students look at this force diagram and they go, aren't you missing something? Didn't we leave out a force? Don't the forces have to balance? And they don't, right? Forces do, there's no rule that forces have to balance out. So these two forces are canceling the effect of each other. But here, there's just a braking force. There's nothing pushing the car forward. The car has a forward velocity. So if we go back here, see that velocity vector, which I should have drawn. There's a velocity vector here and velocity. Those are not forces. That's kinematics. So the force that we are using here is a frictional force that's going to slow us down. Now, the energy transfer, and I'm doing this as an absolute value for just a minute here, the energy that needs to be transferred out equals the existing kinetic energy. How much kinetic energy does that object have? Because that's the energy that needs to be transferred out. So that says that the frictional force times d, now that had a minus sign, but I've suppressed the minus sign. The amount of energy taken out equals the current amount of energy. And that's just the way I set up the equation. Now, they're complicating things here a bit. What they're doing is, first of all, let's say that we're using static friction to slow the car down. that would say the maximum static friction force is mu sub s times n, and the what. So this is independent of velocity. That's all we want to say here, is that the static frictional forces, we're going to model those as being constant forces independent of how fast the car is going. So if that's the case, then I can take the equation we've derived here, and I can write it down twice. I can say F times D1 is equal to 1/2 M1 M V1 squared, and force D2 is equal to 1/2 M V2 squared. So I'm saying, again, the energy taken out by the friction equals the kinetic energy currently in the car. Now I'm going to use ratios. I'm going to flip that around, and the F's cancel, the M's cancel, the 1/2 cancels. I'm going to get D2 divided by D1 is equal to V2 over V1 squared. And so what's happening here then is I can take the two velocities, the 120 and the 60, and take that ratio. I don't have to change units, because the units, if I'm using ratios, the units will cancel out. The units are going to take care of themselves here. So I can square that, and the ratio of 120 to 60 is a ratio of 2, no matter what units I work in terms of. So that's going to be a factor of 4. So if we increase the velocity, and that's the final statement here of the ratio of stopping distances. If you double the speed, stopping distance goes back by a factor of 4. I think this is like a question they use at the DMV, right? Anybody been to the DMV recently and had to take the written exam? I think they asked something like that to remind people that doubling the speed really extends your stopping distance. Your stopping distance is 4 times, your stopping distance at 40 miles an hour is 4 times as much as at 20. So again, a reminder to pay attention to how fast you are traveling. Okay, I think, boy, that's our last example. I think we're down to our last example here. And then in terms of time, we're doing pretty good. I think we might wrap things up a bit early. We'll see. I know I always say that, and then it doesn't necessarily happen, but let's try this. And so what we've got now is we've got a compressed spring. And so what we've done is I think this is the story. That's a lot to read. A horizontal spring has a spring, oh, there we go, there's the K value. Spring constant is 360 newtons per meter. That's not too terribly stiff. How much energy is, how much work is required to compress it? So how much energy will be required and how much energy will we store if we compress it by 11 centimeters? Okay, so that's that's 11 centimeters. And then a 1.85 kilogram block is placed against the spring, and then everything is released. What will be the speed of the block when it separates from the spring and then repeat it? But assume the block is on the... Oh, so with and without friction. Got it. Okay, so... or some kind of a drag force. All right, so I hope I read that carefully. So here's the picture. And what will happen is I'm going to compress the spring, and then I'm going to release this block. Now, the forces are going to be mgn. The spring is going to be pushing with a force of kx. I'm thinking in terms of the block here. The block will experience a force, k times x, due to the spring pushing on it. And then the frictional force is going to slow the process down. Now in part A there is no friction, and in, I think, A and B there is no friction. In part C we come back and calculate it with a 7 Newton drag force, a resistive force. So here we go. When I compress the spring, I will store up energy. And the energy stored here is going to be represented by work. 1/2 kx squared. Now, that stored energy, 1/2 kx squared, works out to be just 2.18 joules. Not a lot. So I've got a little over 2 joules of potential energy stored up in the spring. Now, the mass of the block is 1.85 kilograms. The kinetic energy that the block acquires will be equal to the work, 2.18 joules. So we've stored energy in the spring. When we release the system, all the energy that we stored is going to go into pushing that block. So I don't have to draw, well, I did, kind of. I drew this force diagram, but I didn't really need to draw it with all that detail. So the kinetic energy, the stored energy in the spring is all going to show up as kinetic energy in the block. Now the kinetic energy formula is 1/2 mv squared. So I can take this formula and solve it for v. When I solve it for v, it's 2 times k over m, and then I have to remember the square root sign. Don't forget the square root sign. And putting all those numbers in, it says that that's enough energy to take a 1.85 kilogram block and bring it up to a speed of 1.53 meters per second. So there you go. So energy transfer calculations into the spring, and then energy coming back out of the spring and being used to accelerate a block. Now, in part C, they're going to come back and say, what happens if we now add a resistive force? I'm just going to write it as if it were friction. Now, what's going to happen here is that energy will be taken out. The minus sign's really just saying energy is taken out. And that's 7 newtons is what they told us, times the 11 centimeters. That's going to be 0.77 joules is taken out while the object is being pushed. While the spring expands, 0.77 joules is being taken out. And that says that that's going to become thermal energy. So instead of having the full 2.18 joules of kinetic energy, the kinetic energy we have will be reduced down to 1.41. So now I've only got 1.41 joules of kinetic energy. That also can go into my velocity formula, 2k over m square root. And now I'm not going as fast. I'm only traveling 1.23 meters per second, and the remaining energy has gone thermal. So I've generated a little bit of thermal energy instead. Okay, so another good example. A lot of good examples in here. So we'll be that wraps up chapter 7. We are going to be looking at energy again in chapter 8. So we're going to pick up a lot of the stuff that we talked about in this chapter, and that is going to get used in chapter 8 when we look more generally at using energy techniques in problem solving. The kinetic energy formula, that's going to stay with us for a good long time. The work energy transfer formulas are mostly going to show up. Well, those are going to stay with us too, I guess. So looking ahead, we're going to be making use of all this stuff. So I think we are going to wrap up a little early. If you guys have questions, stop by office hours, and we will get any of those questions looked at as needed.